Start of Slide 1. Slide Caption. Chapter 22. Semiconductor Amplification and Switching. Section 22-1. Amplification. Section 22-2. Operational Amplifiers. Section 22-3. Field Effect Transistors. Section 22-4. Troubleshooting Insulated Gate Bipolar Transistors. End of Slide 1. Start of Slide 2. Slide Caption. Objectives. Section 22-1. Amplification. Define amplification and explain gain. Define and describe transistors. Describe transistor bias and current flow. End of Slide 2. Start of Slide 3. Slide Caption. Two or more amplifiers can be used to obtain the required gain if a single amplifier does not provide enough gain to increase the output signal to the amplitude needed. See Figure 22-1. Often, a single amplifier does not provide enough gain to increase the output signal to the amplitude needed. In such a case, two or more amplifiers can be used to obtain the gain required. For example, amplifier A has a gain of 10 and amplifier B has a gain of 10. The total gain of the two amplifiers is 10 times 10, or 100. If the gains of the amplifiers were 8 and 9, respectively, the total gain would be 8 times 9, or 72. Amplifiers connected in this manner are called cascaded amplifiers. For many amplifiers, gain is in the hundreds or even thousands because signals can be as weak as a few microvolts and may need to be amplified to a few volts. That would require about a gain of 1 million times the original signal size. End of Slide 3. Start of Slide 4. Slide Caption. A PNP bipolar junction transistor is lab-built by doping a thin layer of N-type material between two layers of P-type material in a single semiconductor crystal, whereas an NPN transistor is formed by doping a thin layer of P-type material between two layers of N-type material. See Figure 22-2. There are many types of semiconducting devices that can switch or amplify. Here, one such device is the bipolar junction transistor, or BJT. A BJT is lab-built to have one of two internal alternating polarities. A single crystal can be doped to become either a PNP or an NPN transistor. Those polarity-doped sections of each of their single crystal structures can be used to amplify or switch voltage and current, depending on the circuit in which it is used. PNP transistors switch or amplify positive voltages and currents, while NPN transistors switch or amplify negative voltages and currents. When a PNP switches voltage from a positive power supply source, it is said to be sourcing. When an NPN switches voltage from a negative power supply, such as a negative ground, it is said to be sinking. End of Slide 4. Start of Slide 5. Slide Caption. The three basic BJT amplifiers are the common emitter, common base, and common collector. See Figure 22-3. A BJT can accept an input signal at either its base or its emitter and can deliver an output from either its collector or its emitter, depending on the circuit configuration. This can seem a little confusing, but just remember, each amplifier is named after the transistor connection that is common to both the input and the output load. For example, the input of a common emitter circuit is across the base and emitter, while the output to the load is across the collector and emitter. Thus, the emitter is common to the input and load in this example. To simplify determination of what is common, just remember that whatever pin is not the input or the output is the terminal that is common to that amplifier configuration. End of Slide 5.
Start of Slide 6. Slide Caption. Transistors have either 2 or 3 leads extending from their case. See Figure 22-4. These case packages are accepted industry-wide regardless of manufacturer. When a transistor with a specific shape must be used, a transistor outline known as capitals TO number is used for reference. A popular case is the TO5 package, for instance. End of Slide 6. Start of Slide 7. Slide Caption. A transistor outline, TO, number is a number determined by the manufacturer that represents the shape and configuration of a transistor. See Figure 22-5. Transistor outline numbers are determined by individual manufacturers. Note, the bottom view of a transistor inside a TO3 packaged case shows only two terminal lead wires. Typically, transistors use the metal case as the collector pin lead. End of slide 7. Start of slide 8. Slide caption: in a transistor circuit, the base/emitter junction must always be forward biased and the base/collector junction must always be reverse biased. See figure 22-6. The external voltage, bias voltage, is connected so that the positive terminal connects to the P-type material, base, and the negative terminal connects to the N-type material, emitter. This arrangement forward biases the base/emitter junction. Current flows from the emitter to the base. The action that takes place is the same as the action that occurs for a forward-biased semiconductor diode. End of slide 8. Start of slide 9. Slide caption: in a BJT transistor, an entirely different current path is created when both junctions are biased simultaneously compared to when each junction is biased separately. See figure 22-7. The input voltage to a BJT amplifier or switching circuit is applied between the base and emitter, across the forward-biased base to emitter junction, across which the strength of the input signal freely causes injection of current carriers, either electrons or holes, into the base region of the transistor. Because the base is both thin and lightly doped, not many of the injected carriers make it through the base as emitter base current, the rest are left in the base region. Keep in mind that the base is both part of the forward-biased BE junction and is also part of the reverse-biased BC junction, so most of the current carriers injected by signal into the base are caught up in the much larger current through the collector, attracted by the higher voltage at its terminal. Only signal-injected current carriers enter the reverse-biased BC junction. These current carriers were multiplied by the current gain specification at the amplifying base. The base collector, or BC junction, is reverse biased to prevent current flow unless multiplied current carriers proportional to the input signal are injected through the thin base region and into the collector, where the reverse bias BC junction voltage completes the path back to the power supply. So, even a little emitter to base stimulus current becomes a gain multiplied emitter to collector current through the amplifier or switching circuit. Emitter collector current is the sum of emitter base current and base collector current. The load resistor limits the current flow to a safe level to protect the transistor from damage, while superimposing an Ohm's law voltage across the load that is proportional to the current flow through it. That voltage can be used as the output from the amplifier or switching circuit. End of slide 9. Start of slide 10. Slide caption: 22-1. Checkpoint. What is the total gain of 3 cascaded amplifiers if the first amplifier has a gain of 10, the second has a gain of 5, and the third has a gain of 10? In a common emitter amplifier, the emitter is common to what two parts of the circuit? When a transistor uses its metal case as one of its 3 leads, which lead is the metal base? When the base/emitter junction of a transistor is forward biased and the base/collector junction is reversed biased, is the current flowing through the junctions from positive to negative or negative to positive? End of slide 10.
Start of slide 11. Slide caption: Objectives. Section 22-2. Operational amplifiers. Define operational amplifier, op-amp, and describe its symbol. Explain how an op-amp operates. Describe how op-amps are used. End of slide 11. Start of slide 12. Slide caption: Types of operational amplifiers, op-amps, include dual power and high current, high power op-amps. See figure 22-8. An operational amplifier, also known as an op-amp or just OA, is one of the most widely used integrated circuits. An op-amp is a high-gain, directly coupled amplifier that uses external feedback to control response characteristics. End of slide 12. Start of slide 13. Slide caption: The schematic symbol for an op-amp includes inverting and non-inverting plus inputs. See figure 22-9. The schematic symbol of an operational amplifier may be shown as a triangle with the 2 inputs on one flat side of the op-amps, with a minus sign as inverting and a plus sign as the non-inverting input. The 2 inputs are usually drawn with the inverting input at the top. The exception to the inverting input being at the top is when it would complicate the schematic symbol. In either case, the two inputs should be clearly identified on the schematic symbol by plus or minus symbols. End of slide 13. Start of slide 14. Slide caption. While voltage sources for op-amps can be single supply, they are usually bipolar or dual supply. See Figure 22-10. Like other solid-state devices, integrated circuits, known as ICs, need DC operating voltages to make them work. The DC voltage pins on some ICs are labeled common collector voltage, as in the abbreviation V with a subscript of CC. Other pins are labeled input voltage, as the abbreviation V with a subscript of IN, or supply voltage, abbreviated as V with a subscript of SS. DC voltage ratings in IC databooks are labeled all three ways. The voltage source for op-amps can be single supply. However, they are usually bipolar, also known as a dual supply. End of slide 14. Start of slide 15. Slide caption. Internally, an op-amp consists of a high-impedance differential amplifier, a high-gain stage, and a low-output impedance power output stage. See Figure 22-11. The differential amplifier provides for a wide bandwidth of frequencies it can handle and a high impedance at each input pin. The high-gain stage boosts the signal voltage level considerably. The power output stage isolates the gain stage from the load and provides power with a very low output impedance that allows for a high current drive capability without much voltage drop. End of slide 15.
Start of slide 16. Slide caption. An amplifier is operating in a unity gain condition when the output voltage is an exact reproduction of the input voltage. See Figure 22-12. A voltage follower, or source follower, is a non-inverting amplifier. The output voltage, or Vout, is an exact reproduction of the input voltage, Vin. The function of the voltage follower is identical to that of the source follower created by a bipolar transistor and FET. The circuit is used to impedance match an input signal to its load. With the voltage follower, the input impedance is high and the output impedance is low. It should be noted that the voltage follower has no input or feedback components. Because no feedback components are used in this type of circuit, the amplifier is operating in a unity gain condition, where unity gain means an amplification factor of 1, meaning the same voltage comes out as what goes in. End of slide 16. Start of slide 17. Slide caption. Closed loop systems may be depicted by block diagrams. See Figure 22-13. To achieve automatic control, interaction between the control unit and the controlled element must occur. In a closed loop system, this interaction is called feedback. Feedback can be activated by electrical, thermal, light, chemical, or mechanical energy. Both full and partial control can be achieved through a closed loop system. End of slide 17. Start of slide 18. Slide caption. A feedback inverting amplifier produces a 180 degrees phase inversion from input to output. See Figure 22-14. In this configuration circuit, when a positive going voltage is applied to the input, a negative going voltage will be produced at the output because the input signal is applied to the op-amp inverting input through R1, while resistor R2 serves as the feedback element. The output voltage will be the opposite polarity of the input voltage and the voltage level will be that of the input voltage times the ratio of R2 divided by R1. End of slide 18. Start of slide 19. Slide caption. As the ambient temperature around a thermistor changes, the resistance of the thermistor changes. See Figure 22-15. A thermistor varies the amount of input current, symbolized as capital I, with a subscript of In, that enters the inverting input of the op-amp. As the ambient temperature around a thermistor increases, the resistance of the thermistor decreases, current to the input of the op-amp increases, and voltage at the output increases. As the temperature decreases, the resistance increases, current decreases, and voltage output decreases. Since the output of the circuit is now voltage, the op-amp voltage can be used to drive an output device. End of slide 19. Start of slide 20. Slide caption, a voltage to current op-amp can be used to control an air compressor. See figure 22-16. In certain circuits, such as a circuit in an air compressor, a change in voltage becomes the reference for the change in the circuit. When this is the case, a voltage to current op-amp is used. The output voltage of the bridge circuit is a function of the degree of imbalance present in the input bridge. For the bridge circuit, an imbalance can be created by changing the pressure on the pressure sensor transducer. The potentiometer determines the pressure set limits. End of slide 20.
Start of slide 21. Slide caption. A differential op-amp can be used in a solar water heater thermostat control circuit. See figure 22-17. An op-amp can be used as a differential amplifier. A differential op-amp is a type of op-amp used in differential thermostat controls for solar water heaters. Small signal changes can be detected easily in the circuit and are amplified for signaling or control purposes. Because the output of an op-amp has very little power output capabilities, an interface device, such as an amplifier or control relay, must be used to control higher power loads, such as a water pump in a hot water system. End of slide 21. Start of slide 22. Slide caption. 22-2. Checkpoint. Why is an op-amp better for amplifying a very small signal to a larger signal than using a transistor as the amplifier? Why do op-amps draw very little power from the input source they are going to amplify? What type of op-amp is used to take a very small amount of input current and produce a much larger voltage output? What is an example of an interface device that can be connected between the output of an op-amp and a pump motor? End of slide 22. Start of slide 23. Slide caption. Objectives. Section 22-3. Field effect transistors. Define field effect transistor known as FET and list the different types. Define and describe a junction field effect transistor known as JFET. Define and describe a metal oxide semiconductor field effect transistor known as MOSFET. Define and describe an insulated gate bipolar transistor known as capitals IGBT. End of slide 23. Start of slide 24. Slide caption. The arrow in a schematic symbol for an N-channel JFET points inward. The arrow points outward for a P-channel JFET. The arrow always points toward the N-type material in any semiconductor. See figure 22-18. A junction field effect transistor or JFET is a simple FET with a PN junction in which output current is controlled by an input voltage. All FETs are voltage-controlled devices, whereas BJTs are current-controlled devices. Just as there are PNP and NPN bipolar junction transistors, the two types of JFETs include the N-channel and P-channel. Just as ABJT contains pins known as emitter, base, and collector, a JFET, like all FETs, contains a gate, G, a drain, D, and a source, S. The gate is a control element, while the drain and source provide the same function as the emitter and collector on a bipolar junction transistor. End of slide 24. Start of slide 25. Slide caption. The output current of a JFET is controlled by an electrical field created by the input voltage. See figure 22-19. A JFET is a unipolar device. This means that the channel through which charge carriers can flow from source to drain is made of a single polarity material, either N or P-type material. A JFET, which differs in operation from a bipolar junction transistor. The output current of a JFET is controlled by the voltage on the gate with respect to the source. The gate voltage creates an electrical field, or that depletes the channel region of many free charge carriers between the source and drain. Again, the JFET is considered a voltage-driven device rather than a current-driven device like the bipolar junction transistor. End of slide 25.
Start of slide 26. Slide caption, a JFET characteristic curve shows the operating characteristics of a JFET. See figure 22-20. On a JFET characteristic curve, the drain-to-source voltage, abbreviated as capital V with a subscript of ds, is plotted along the horizontal axis. The drain current, abbreviated as a capital I with a subscript of D, is plotted along the vertical axis on the characteristic curve for a typical N-channel JFET. By using one curve, the detailed information produced may be more readily obtained at any operating point chosen along the curve. End of slide 26. Start of slide 27. Slide caption: in a common source JFET circuit, the input is across the gate and source terminals and the output is across the drain and source terminals. See figure 22-21. JFETs can be connected into three basic circuit configurations: common source, common gate, and common drain. Common gate and common drain circuits are constructed in a similar common element arrangement. Furthermore, the only difference between an N-channel and P-channel circuit configuration is the direction of electron flow in the external circuit and the polarity of the bias voltages. You may remember from the earlier slide on the BJT, whatever pin is neither input nor output is what is common. That goes for both BJTs and JFETs. End of slide 27. Start of slide 28. Slide caption: a digital multimeter can provide high input impedance with good sensitivity by using a JFET in its front-end circuit. See figure 22-22. FET multimeters use JFETs to provide high input impedances with good sensitivity. A JFET is capable of producing an input of 11 megaohms or more. In a simple FET multimeter circuit, the JFET is one leg in the DC bridge. Source resistor RS provides negative feedback for high linearity in the response. The circuit requires good regulation, which is provided by a Zener diode. End of slide 28. Start of slide 29. Slide caption: MOSFETs are available in both N-channel and P-channel constructions. See figure 22-23. MOSFETs are available as N-channel and P-channel devices. With an N-channel MOSFET, the arrow on the substrate points toward the channel. With a P-channel MOSFET, the arrow on the substrate points away from the channel. End of slide 29. Start of slide 30. Slide caption: a positive voltage applied to the upper plate of a capacitor causes the dielectric to become distorted, with the electrons moving in the direction of the positive plate. See figure 22-24. Holes are cut into the silicon dioxide insulating material, allowing contact with the N-type regions and thereby connecting the source and drain leads. The MOSFET construction is complete when a polysilicon contact gate is placed over the insulating material in a position to cover the channel from source to drain. End of slide 30.
Start of slide 31. Slide caption: the broken line in the schematic symbol indicates that the MOSFET is normally off. See figure 22-25. When the gate has zero voltage or a negative voltage, no enhancement effect is possible and the MOSFET does not conduct. Since the enhancement MOSFET does not conduct at zero gate voltage, it is often called a normally off MOSFET. In the schematic symbol, a broken line between terminals indicates the channel. The broken line signifies that the MOSFET is normally off and must be enhanced to conduct with a more forward-biased voltage across the gate to source terminals. MOSFETs with that broken line for the gate are called enhancement mode MOSFETs. MOSFETs with a solid line for the gate symbol are usually called depletion mode MOSFETs because they normally conduct from source to drain and must be depleted of free charge carriers in the channel. Some MOSFETs are considered both enhancement and depletion mode devices because they are in the middle between these two extremes. You must consult your manufacturer's datasheets to determine which is which and how to use them properly in various circuit applications. End of slide 31. Start of slide 32. Slide caption: a depletion enhancement MOSFET has the addition of a physical conducting channel between the source and the drain. In the depletion mode, a negative voltage is applied to the gate. In the enhancement mode, a positive voltage is applied to the gate. See figure 22-26. The polarity of the voltage across the gate to source really depends on whether the arrow points toward or away from the channel region in the schematic symbol of the MOSFET you are using. If the arrow points in, then the channel is negative. If the arrow points away from the channel, then the channel is positive. You must apply the polarity to the gate that is the corresponding polarity if you want to run the device in enhancement mode or depletion mode for any MOSFET. Again, always consult the manufacturer's data sheet for such information, as well as the voltage values to be used. End of slide 32. Start of slide 33. Slide caption. Current through a dual-gate MOSFET can be cut off by either gate. See figure 22-27. A MOSFET can be constructed with two gates, such as in a dual-gate MOSFET arrangement. Current through the MOSFET can be cut off by either gate. A MOSFET also operates on the capacitive effect. End of slide 33. Start of slide 34. Slide caption. A DMOS power MOSFET contains an inherent p-n junction diode. Its equivalent circuit can be considered as a diode in parallel with the source-to-drain channel. See figure 22-28. This DMOSFET has a built-in diode that can protect the DMOSFET from counter EMF or other transients that might otherwise damage the DMOSFET. End of slide 34. Start of slide 35. Slide caption. An insulated gate bipolar transistor is also known as the IGBT, which is a three-terminal switching device that combines an FET with a bipolar transistor. See figure 22-29. The problem with most BJTs is that they require current input to get current out of them that is related to their current gain factor. And the current gain of power BJTs is usually very low compared to low power BJTs. As a result, it takes a lot of emitter base current to get high current out of a powerful BJT. But high-power MOSFETs are voltage-controlled devices and do not require much, if any, current to control them. So, it makes sense to build a transistor that combines the benefits of transistor technologies. By putting a high-power MOSFET on the input to the power BJT, the input to the MOSFET will not demand high current, because the voltage-controlled MOSFET will deliver that current based on the voltage on its high-impedance input, and the power BJT will then deliver the high current output that is required to the low-impedance load. This IGBT solves the weaknesses of the power BJT by introducing the power MOSFET on its input. Factory miniaturization also means that all this can be made within a single package rather than needing to build a circuit from two or more different components to accomplish this. That is great. End of slide 35.
Start of slide 36. Slide caption. The main difference between a power MOSFET and an IGBT is the addition of an injection layer in the IGBT. See figure 22-30. This is a highly technical, yet subtle difference. Due to the presence of the injection layer, current carriers called holes are injected into the highly resistive N layer and a carrier overflow is created. This increase in conductivity of the N layer allows the reduction of the on-state voltage of the IGBT, which overcomes many issues that would not be available without this extraordinary technology. High-power MOSFETs and IGBTs are a couple of my favorite electronic devices for powerful robotic controllers. End of slide 36. Start of slide 37. Slide caption, 22-3. Checkpoint. In the symbol for a JFET, if the arrow on the gate is pointing out of the device, is the JFET an N-channel or P-channel type? In figure 11-4, if an output load is connected to an N-channel JFET, the load would be connected to the source gate in which polarity of the power supply. What type of MOSFETs are designed to switch higher current loads? Are IGBTs available to switch high voltages and power such as a 480 volts, 450 watt loads? End of slide 37. Start of slide 38. Slide caption, Objective. Section 22-4. Troubleshooting insulated gate bipolar transistors. Explain how to troubleshoot an insulated gate bipolar transistor, IGBT. End of slide 38. Start of slide 39. Slide caption, the leakage resistance between the gate, G, and emitter, E, is measured with the collector, C, and emitter, E, shorted to each other on an IGBT. See figure 22-31. When a digital multimeter DMM is used, the internal battery voltage should be verified to be less than 20 volts. A high voltage can damage the IGBT. The resistance reading for an IGBT in good condition ranges from several megohms, m, to infinity. The IGBT is considered defective if the resistance between the gate and emitter is very low. End of slide 39. Start of slide 40. Slide caption: the resistance between the collector, C, and emitter, E, is measured with a jumper between the gate, G, and emitter, E. See figure 22-32. The collector should be connected to the positive, red, test lead and the emitter to the negative, black, test lead. The DMM resistance reading should range from several megohms to infinity. The IGBT is considered defective if the resistance between the collector and emitter is very low. There are many advantages of IGBTs. The main advantages of an IGBT are the following: low on-state voltage drop, possibility of small chip size, low driving power, simple drive circuit, wide SOA. End of slide 40. Start of slide 41. Slide caption: 22-4. Checkpoint. When measuring the gate to emitter resistance of an IGBT, is a high or low resistance expected if the device is good? When measuring the collector to emitter resistance of an IGBT, is a high or low resistance expected if the device is good? End of slide 41.
Copyrights originated by the publisher with modifications by Nita Layton and Glenn Graham.